Good evening. Welcome to another question in biology. So let's start and see what we can get out of it. So I'll begin by introducing data-based equations. I've already done two data-based equations, the one of 2001 and the one for 2002. Now I'm doing the data equation of the year 2003. So these data equations serves to make concepts learned in theory and practical clearer, motivate further thinking, and making biology relevant in day-to-day living experiences. The video is designed to develop the ability to do guided manipulations, paying attention to the importance of step-by-step approach, understanding the procedure, examining the data, and making the correct observations. All plotting the data, if a graph is needed, after carefully choosing the correct scale, drawing smooth curves with free hands, and making right decisions to answer the questions using information given in the data or in the graph. The video will not be of any help if the questions are not done and the work is treated through theory approach. You develop analytical skills by practicing them. This is the only way you become aware of your strengths and weaknesses in biology data questions. The question of 2003 on data was question 17, and the total mark envisaged to be scored was 20 marks. So the question was as follows. Some students used a model to demonstrate the effect on human body temperature. Two boiling tubes A and B were filled with hot water. The temperature of water in the tubes was taken at the start of the experiment and then at a 5-minute interval. The surface of the tube A was continuously wiped with a piece of cotton wool soaked in methylated spirit. The results obtained are shown in the table below. The results obtained are shown in the table below. Time in minutes, temperature, degrees Celsius in tubes. So you can see 0 minutes, the temperature was 80. We are equal temperatures. After 5 minutes, A and 54, B 67. 10 minutes, A 40, B 59. 15 minutes, 29 for A, 52 for B. 20 minutes, 21 for A, 47 for B, and finally, after 25 minutes, 18 for B for A and 46 for B. On the same axis, plot graphs of the temperature of water in tubes against time. At what rate was the water cooling in tube A? Why was tube B included in the setup? Account for the rate of cooling in A. State the two processes of heat loss in tube B. What would be expected results if tube A was insulated? What would be the insulation comparable to in birds, mammals? And the last question is, name the structure in the human body that detects external temperature changes. And Roman 2, internal temperature changes. So let's look at the approach. How are you supposed to approach this question? So, have you ever wondered how a simple household substance could dramatically affect the cooling rate of hot water? What if I told you that a common item could help us understand a fundamental principle of temperature regulation? Stay tuned to discover how methylated spirit can reveal surprising insights into cooling processes. In this video, we will transform raw data into clear, actionable insights. By analyzing our experiment, you will not only see how evaporation influences temperature, but also learn how these principles apply to the real-world scenarios, from everyday cooling techniques to advanced scientific applications. To make sense of our results, we will plot the temperature data from both boiling tubes on a graph. This will help us visualize how continuous wiping with methylated spirit accelerates cooling compared to a tube left untreated. By the end of this video, you understand the science behind these observations and how they connect to broader concepts of heat transfer and cooling in various contexts. How do we approach the first question? And therefore, let's look at the way we will guide the students, or for the teachers, for that matter, in guiding students on drawing the graph. 1. Read the table carefully. Identify the independent variable, time in minutes, and the dependent variable, temperature in degrees centigrade. Separate the data for tube A, wiped with methylated spirit, and tube B, no wiping. Number 2, set up the axis. X-axis. Label the x-axis as the time minutes or time in minutes, since time is the independent variable, so it goes to the x-axis. Choose an appropriate scale based on the intervals, e.g. 0, 5, 10, 15, etc. Y-axis. Label the y-axis as temperature in degrees centigrade. Since this is a dependent variable, select a scale that accommodates the full range of temperatures observed in the table. So independent variable goes to the x-axis, dependent variable goes to the y-axis. Number 3, plot the points. For tube A, wiped with the spirit, plot each time against the corresponding temperature on the graph using a specific marker, e.g. dots or crosses. But as I told you the other time, I prefer crosses because they are more accurate. For tube B, control, not wiped. So tube B is a control experiment, which is not wiped. Plot the time against the temperature using the different marker or color to distinguish the two data sets. Number 4, draw the curves. Connect the points for tube A with a smooth line, showing how the temperature changes over time. Do the same for tube B, ensuring the two curves are clearly distinguishable. Number 5, label the graph. Title the graph as temperature of water versus time for tubes A and B. Clearly label which curve represents tube A and which one represents tube B. Underrated or key if different colors are used. Number 6, analyze and compare. Look for differences in how the temperatures in the two tubes changes over time. Students should notice that tube A, wiped with methylated spirit, cools faster than tube B, as the evaporation of the methylated spirit causes rapid heat loss. So there is the graph of temperature of water in tubes against time. So in that graph, you mark it as follows after plotting. For this graph, I never used different colors. I used just the same colors, but I labeled. So you can use different colors or label the graph. So plotting a mark for both graphs. Curve, smooth curve, have a mark for both graphs. Labeling our identity of the curves, have a mark for each diagram. Labeling of the x-axis, time in minutes, a mark, and labeling of y-axis, temperature in degrees centigrade in tubes, a mark. So scale have for each curve, which is one mark. Smooth curve have a mark each, which is one mark. Plotting P, 2 marks. Axis A, 2 marks. Identity have a mark each, which is 1 mark. Reversed axis, maximum 2 for scale and identification. That is, if you put time in y-axis and temperature in x-axis, that is reversed. So you get just a maximum of 2 marks for scale and identification. Wrong scale, maximum 3 for axis and identification. No origin, deny have mark only. All right. Let me see. I'm trying to read that one. Penalize scale only once. 2 separate graphs. Mark first one only, maximum 4. Deny labeling of vertical axis and vertical scale. Those are the writings I'm trying to read there, and I hope you have followed me, and so you have no problem even if you are using a mobile phone. At what rate was the water cooling in tube A? So get 80 minus 18 over 25, which is 62 over 25, which is 2.48 degrees centigrade per minute. 80 is the temperature at the beginning when you start, and 18 is the temperature at the end. That is after 25 minutes. So you subtract and you divide by 25. The total number of minutes, you get the rate. All right. Why was tube B included in the setup? This is just a control. Account for the rate of cooling in tube A. Rate was faster in tube A because the film of methylated spirit evaporated, removing heat from the tube. State 2 processes of heat loss in tube B: convection and radiation. What would be the expected results in tube A if tube A was insulated? Lower rate of heat loss, lower rate of heat loss. Comparison must be there. Lower. Okay. Fine. What would be the insulation comparable to in birds, feathers, mammals, hair, or fur? I think it is fur, sorry. So I hope I've explained there. All right. That is, at what rate was the water cooling in tube A? And I said 80 is the temperature at the beginning, and 18 is the temperature after 25 minutes. So to get the rate, get the difference and divide by 25, the total time taken, you get 62 over 25, which is 2.48 degrees centigrade per minute. And I have also said tube B was included in the setup as a control experiment. And I have also accounted for the rate of cooling in tube A, and the rate was faster in tube A because the film of methylated spirit evaporated, removing heat from the tube. I also stated 2 processes of heat loss in tube B, and these are convection and radiation. For F, what would be the expected results in tube A was insulated? You would have lower rate of heat loss, but here you must give a comparison. Lower rate of heat loss. What would be the insulation comparable to in birds, feathers, in mammals, fur, or hair? Name the structure in the human body that detects external temperatures. We have temperature receptors, but you can use all these other ones like end of bulb capsules, bulbs of clouds, organs of Lufini. But I don't think most of us will remember these ones. Just say temperature receptors, accept heat or thermal receptors. Internal temperature changes, hypothalamus detects. What we learn from this experiment in daily life. This experiment models evaporation and its effect on cooling, simulating how the human body regulates temperature. Point number 1, cooling mechanism of sweating. In real life, the human body cools itself by sweating. Sweat evaporates from the skin surface, removing heat and lowering body temperature, similar to how the spirit in tube A speeds up the cooling process. Role of evaporation in daily activities. Evaporation is key in keeping cool in hot environment. We naturally lose heat by sweating, and wiping or fanning can speed up this cooling, especially if air circulation or substances like alcohol, which evaporates faster, are involved. Practical applications. This understanding helps in making informed decisions such as wearing light, breathable fabrics in hot weather to enhance evaporation and stay cool. It also highlights the importance of hydration, as water is needed for sweating and regulating body temperature. In essence, students learn the scientific principles behind everyday experiences like sweating, cooling, and temperature regulation, and how these can be practically applied for comfort and health. I would have forgotten to make the acknowledgements. The work is truly a team effort. There are too many people who inspired me to come up with production of this video, and I thank them with all my heart. I would also thank my family members for their support, encouragement, patience, and tolerance during my long hours of typing the PowerPoint presentation. I'm grateful to all the individuals who commented positively when the final video was launched, and the third party whose material has been used in this book. And the third party whose material has been used in this video. Every effort has been made to contact all the copyright holders, but if any have been inadvertently overlooked, I will be pleased to make the necessary arrangement at the earliest opportunity. This video may not be reproduced in any form whatsoever, in part or in whole, without the express permission of the compiler and designer. Special thanks to ChatGPT, an AI language model developed by OpenAI, for providing assistance with creating and editing the content for this video. Midamo TK. So, thank you guys for watching the video to the end. Don't forget to subscribe this YouTube channel for more amazing and educational content as far as data questions are concerned. Goodbye. and good night wherever you are in Kenya, and also good time, good time, whatever time you are in. Have a good time wherever you are, even if it is during the day. Goodbye, and see you in my next video.